Hi everyone, my name is Dr. Destiny Knock and I am an assistant professor at Carnegie Mellon University in Civil and Environmental Engineering, as well as Engineering and Public Policy. Today, I will be presenting to you about an in-depth analysis of greenhouse gas emissions and air pollutants from electrical transmission and distribution systems. This work is a joint collaboration between myself, so Dr. Destiny Knock, Kavita Sarana, who is at the University of Maryland, and Sarah Jordan, who is at Johns Hopkins University. So the motivation for this is that electricity is highly linked to development. So in the United Nations Sustainable Development Goal 7, there is the desire to ensure access to affordable, reliable, sustainable modern energy for all. Now, on the right-hand side of this graph, you are looking at the Human Development Index versus per capita electricity consumption in 2014. So the Human Development Index is a composite statistic of life expectancy, education, and per capita income indicators created by the United Nations. And each dot on this graph represents a different country. So while this graph is showing a correlation, not a causation, there is no low energy, high income country. So while correlation is not causation, governments are deciding to build electricity systems because of the links that we see with human development. So when you're thinking about building out a sustainable electricity system, this can happen at multiple levels. There's the power plant level. So this would be the high generators, wind turbines, solar panels, etc. Then there's also the consumer level. So thinking about putting rooftop solar, battery systems, or even deploying electric vehicle technologies at the individual scale. Then in the middle of all this, we have the electricity grid, or the transmission and distribution system. So the transmission distribution system is everything that's linking those power plants to the household consumer level. And countries are really starting to think about how these three different stages of the power system impact their air pollution emissions. In 2010, approximately 40% of global CO2, 48% and 40% of global sulfur dioxide emissions were linked to the power sector. So as countries are thinking about building this grid as we move to our Sustainable Development Goal 7, they are working in the Paris Climate Agreement to think about what efforts they can make at a country level. So within the Paris Climate Agreement, each country made an NDC, or a nationally determined contribution, that embodied their efforts by each country to reduce the national emissions and adapt to the impacts of climate change. When we looked at this, so this graph is showing you on the y-axis a log of emissions from electricity generation on the y-axis, and on the x-axis you have the transmission and distribution losses as a percentage of electrical consumption in the country. Green dots are countries that mention their transmission and distribution losses in their original NDCs, and gray dots are countries that do not mention transmission and distribution losses in their original NDCs. So if you're looking at the green dots, only 32 countries have mentioned grid efficiency in their climate change mitigation strategies. In contrast to this, we have seen that 110 different countries mention some form of renewable energy. So this highlights that generation is often the focus as opposed to efficiency in transmission and distribution systems. And when we think about efficiency, we really are talking about lowering the percent of transmission distribution losses on that x-axis. With inefficient transmission systems, the reason we care about this is because this leads to inefficiencies in other sectors. So let's assume that we have a demand of 100 megawatt hours. And we have one wind turbine that can supply 20 megawatt hours at $45 a megawatt hour. Then a totally efficient system means that we would need to build 5 wind turbines at $4,500. But if we had a transmission and distribution system with 10% losses, or losing 10 megawatt hours for each person's demand that you serve, this would mean that we would need to build an extra wind turbine. So now we have to build 6 wind turbines instead of 5. And this comes at an additional cost of $450. So you can imagine that as we scale up to the country level, this number grows very quickly. So now we're going to talk about the methods that we are going to use for calculating losses on the transmission and distribution system. The transmission and distribution losses, or TND losses, are calculated as a percent of losses by region, which is NTD. And that's going to be equal to the reported transmission and distribution losses at the country level divided by the total electricity generation for each region or country. Then this will correspond to the compensatory generation from the power plant. So this is going to let us find how much extra power did we need to generate because of the inefficiencies in our system. And that's just going to be multiplying the percent TND losses times the electricity generation in that region. When we are thinking about environmental sustainability of our electrical systems, there are many different facets. So we have a shift to renewable resources, which is limiting the consumption of fossil fuels or non-renewable sources, protecting health of the ecosystems, targeting welfare, not GDP. So thinking about different measures for economic and social welfare, and then also intergenerational decisions, such as making economic decisions based on long-term consequences. And last, but certainly not least, that red box is avoiding excess air pollution because of the health and atmosphere damages that we see linked to this type of pollution. And that's where we're really starting our focus. Previous work by Kavita and Sarah, or Dr. Sorana and Dr. Jordan, focused on investigating the CO2 mitigation potential for increasing efficiency of electric transmission and distribution systems. And we can see that the largest potential, or the darkest green squares, are highlighted in China, India, US, and in North Asia. So one of the things that we have decided to build on here is looking at the range of pollutants that are associated with electrical transmission and distribution systems. So this would be, the first one is SOx emissions, because these are linked to more frequent asthma attacks and exacerbation of cardiovascular disease. We are also going to consider NOx emissions due to their increased susceptibility to lung infections in people with asthma, as well as worsened symptoms and airway inflammation in healthy people. And we are also going to be looking at particulate matter. So particulates that are so small they can get deep into the lungs and into the bloodstream. And there's sufficient evidence that exposure to PM 2.5 over long periods can cause adverse health effects. Our emissions calculation is based on life cycle emissions estimations. So life cycle emissions estimations are air pollutant emissions over the lifetime of the power plant. Our emissions calculation, or the E loss, which is equal to the air pollution emissions associated with TND losses, is equal to the sum of our emissions factor, so the air pollution per unit of energy, times the compensatory generation resulting from TND losses, multiplied by K, which is the scaling factor. This scaling factor is used to account for efficiency of different power plants across regions. So for example, a coal plant in the US might have a different efficiency than a coal plant in India. And our data is being sourced from the IEA, using that for world calculations, and the EIA, which is going to be used for our subnational calculations in the US. Now this is a heat map of the different countries, and it's showing you the average percent of transmission and distribution losses across the world. We see a high amount of inefficiencies in Africa, as well as India and Central Eurasia. We also have a high amount of losses in Mexico and South America. Now, the US is pretty low with an average of 6%. India is pretty high with an average of 18%, but the highest is actually Haiti, which is really hard to see on this graph, and that's at 60%. So we see that there's a lot of opportunities for thinking about how making sure that our transmission systems are efficient, and valuing valuing these efficiencies in terms of the air pollution emissions that they could reduce. And the other connection is that transmission inefficiencies translate to overproduction in the generation sector. So the heat map is showing you the sum of transmission losses in gigawatt and terawatts, and the USA is very low. So even though we had really high efficiency, really high efficiency in the US, we see that this still correlates to a lot of losses associated with the transmission system. So China is the highest, again, with 381 terawatt hours, and the US is second with 244 terawatt hours, and then India is actually higher than the US at 261 terawatt hours. So this is going to translate into sulfur dioxide emissions, as we can see here. So these, the bubbles are basically showing you the concentration of these emissions, and the bigger the bubble, the more emissions are there. Looking again at China and the US, we see that we are getting a very high amount of emissions from these countries due to the overproduction. And so this would mean that we need to think about how inefficiencies translate in different contexts, and the value of 1% or 2% efficiencies in these different systems. There's also a connection with air pollutants and TND losses. So on the y-axis, we have the log of our air pollutants from compensatory generation. Then on the x-axis, we have our transmission and distribution losses. And we can see that a lot of times countries, even though the transmission distribution losses are below 20%, they still have a high amount of air pollutant emissions. And then when we get to the countries that are pretty high at 60% of the of the inefficiencies, then we could see that just making these systems really efficient would bring them back over to this curve, and also back over to the left-hand side of this graphic, and kind of help reduce some of their losses that they're seeing. So we see that, so each dot, by the way, is a different country, and we do see that there is a high logarithmic correlation with the TND losses. So this graph is just showing you the sulfur oxide emissions in gigawatt hours on the y-axis, and along the x-axis on the right, that's the transmission distribution losses by percentage. So that's from the previous slide, and then on the other side, the transmission distribution losses are by terawatt hour. And so we do see that there is going to be a lot of countries in this blue curve that are not having transmission distribution losses above 50 terawatt hours. And so this is really showing us that the logarithmic curve is a great fit, and when we can pull in these dots, we're going to go down to the bottom left-hand side of this curve, and that would really help us in reaching our air pollution emissions goals. To look at different countries, we did a Monte Carlo simulation. So we took our emissions calculation, these are the terms, and then we used triangular distributions to estimate how those air pollutant emissions translate into how the transmission distribution losses translate into air pollution emissions for different countries. And we did this for 10,000 trials. So on the left-hand side, I wanted to show you the world SOx emissions, and on the right-hand side, we have emissions for two different countries. The United States is in red and India is in blue. So we see a larger uncertainty in India, and that comes from their dependence on coal generation. There's a larger range in pollution emissions estimations, and this hints at the need for analysis at the subnational scale to understand how regional impacts, how these national impacts could translate down to the regional level. So in conclusion, I've showed you our initial work in thinking about how to evaluate transmission distribution losses at the national scale in multiple countries. This work is really focused on understanding how reducing transmission distribution losses promotes economic efficiency and as well as minimizing emissions and reaching our sustainable development goals. Future work and ongoing work is focused on evaluating the climate mitigation potential at the subnational scale as well and doing a wider sensitivity analysis, so comparing the CO2 emission ranges with our newer air pollutants. Thank you for your time. And this is my contact information. I would like to acknowledge the NSF grant and the Carnegie Mellon Scott Institute for Energy.